Okay, so we are looking at section 6.1. This is kind of 6.1 part 2. And so here we're looking at number 6 from the activity sheet that I gave you last time. Come on over here. Were you here last class, Cam? No. Then you probably need one of each of these, right? Yeah, one. And we're actually on the back of this sheet right now. Okay, so for this one, we're going to set up and use law of sines. And as we're trying to solve this triangle, we're going to try and find out, well, is there no triangle possible, one triangle, or two triangles? So when we set this up, we're going to write this as what? Mary, how should we set this up? All right, so sine of 58 degrees over 4.5
equals sine of b over 5.
Okay, so this is, we don't know the angle b, so we'll write sine of b over the length of b, which is 5. And did we cross multiply? Yes. So we get 4.5 times the sine of b equaling 5 times the sine of 58 degrees.
Is this just like proportions, I guess? So,
I mean, the law of sines looks kind of like proportions.
okay.
And so we divide both sides by 4.5, and then we find out that the sine of angle B is equal to what when we do this? 5 times sine of 58 degrees over 4.5. What did we get?
I think we got 0.942.
Sine of B turned out to be 0.942.
First off,
Alright.
I know it was when you did the arc sine of b, it was 70.4 degrees.
So when we found the arc sine, so to find angle B, we do the arc sine of 0.942, right? And you said that turns out to be 70-some degrees?
Yeah.
So B is equal to 70, what was it?
24.
70.4 degrees. Are we okay with this?
When you're normally doing this, like in problems when they just don't give you the angle, do you always have to use arc sine to find it, or?
Yes. Well, right, because if you're solving for sine of if you're solving for sine of some angle, you're going to be given, sine of angle B or whatever is some decimal value, and you're going to have to use arc sine to find the angle itself. Okay, so with that in mind, that's great. That means we have a triangle possible. So we know it's not no triangle possible. It's either one triangle possible or two. So at this point, let's write down what we have for this. I'm going to call this triangle 1. We know that angle A is 58. Angle B is 70.4. We don't know angle C yet, but I'm sure you're about to tell me what that is. Side A is 4.5, side B is 5, and we don't know what C is. So how do we find angle C, Stephanie?
180 minus 54, 70.4.
All right, so we're adding these two up and subtracting from 180, and that leaves us with what?
51.6.
51.6 degrees, okay, and then how do we find side C, which is our last missing piece here, Josh?
I would just do sine of 58 over 4.5 equals 50, or sine of 51.6 over C.
So sine of A over A, so that's sine of 58 degrees over 4.5 equals sine of 51.6 over C. And then we're going to cross multiply here, and we end up getting C equaling, I guess it'd be 4.5 times sine of 51.6 over sine of 58 degrees. And we did this last time?
Yeah.
And what did we get for C?
4.2.
4.2? 4.2. By the way, I think it's a good thing, we didn't talk about this last time, but I think it's a good thing to check. Remember from geometry, you know that the largest angle is across from the largest side. So here, my largest angle is 70.4. Is 5 the largest out of my sides? Yes. And my smallest angle looks like angle C. Is that across from my smallest side? And get into a habit of doing that check, and you'll be happy you did in section 6.2, because things can get messed up there. Okay, so that's triangle 1. Here we go. This is all triangle 1. But we said maybe it's possible to have triangle 2, question mark. Well, we only know if there's going to be a possible triangle too if we list what we know, which was that A was equal to 58, side A was 4.5, and side B we were told was 5. Is that correct?
Yes.
Hello? She did, yes. Thank you, sorry. It's fine. Okay.
It was excused.
I understand. And I think that if Ms. Hurt doesn't know that.
Yeah.
Okay. Okay, so this is the given information, but then we said there might be another angle whose sine is equal to 0.942, right? And what other angle? And remember, we talked about this. We looked at the unit circle, and we said, here's our unit circle. Let's say here's a y height of, like 0.5, and I can slide this up. Here's a y height of 1, but somewhere there was a height of 0.942, right? And right here is an angle that has that measure, right? 70.4 degrees. But over here is another angle that also has a y coordinate of 0.942. So this angle's got a y coordinate of 0.942, but so does this one. And we found this larger angle by taking 180 minus 70.4, because this angle here and this angle here are going to be congruent. So what's 180 minus 70.4? We did this. Yes?
I got, or not 4.2. Is it? What was it? 4 point, it's not 4.2. I can't find it out here.
We don't remember? We'll go ahead and do it again.
Isn't it 109.6?
109.6?
Yeah.
Okay, so if B is equal to 109.6 degrees, I still don't know if we have another triangle possible. I won't know if a second triangle is actually possible until this step right here where I'm trying to find angle C. Because the three angles have to add up to 180, and I don't know if there's room for this angle C, or if this angle C is going to end up being negative, right? So if I add 58 and 109.6, if that's already over 180, then no second triangle is possible. Does that make sense? So we add 58 and 109.6, and we end up getting what?
167.6.
167.6, and then I subtract that from 180 to get angle C. It's still a positive number, which means the second triangle is possible. What is it going to be?
12.4.
Thank you. So 12.4 degrees is that last angle. Danny?
So if the sine value is less than 1, you can begin to solve for a second triangle.
Correct. You would try and solve for a second triangle. Okay, and then we still need to find a side C, and I'm not sure if we finished this up last class. I think we were just about ready to do that. So we would do sine of 58 degrees over 4.5 equaling sine of 12.4 degrees over C. Did we do this last time?
No.
We ran out of time. So C is equal to 4.5 times sine of 12.4 degrees over sine of 58 degrees. And you're doing this on your calculator, and you're getting what?
I got 1.14.
Do people agree with that? I see Stephanie's got a calculator in her hand. Thank you. Josh does. You got a calculator, Mary? It's charging. Alex, you got a calculator?
I got 1.
What did you just do? I have no idea what you just did.
How to get that answer?
Yeah.
We go to a calculator, put a fraction template. We're going to do 4.5 times. It was sine of, what was it? 12.4 over sine of 58. Sine of 12.4, but I need degrees. Over sine of, whoops, sine of 58 degrees. And we do that and we end up getting 1.14. Looks okay to me. All right, so at this point, 1.14 is our last remaining side length we need to find. So we would call this all triangle 2, and I can get rid of the question marks because it does exist. Are we okay with those? Again, a little check, is our smallest side across from our short, or is our smallest angle across from our shortest side? And is our longest side across from our largest angle? All right, good. Okay, at this point, I think we can skip those. That was just, again, another example of finding 2 triangles that are possible. Let's get to the area of an oblique triangle. This picture is not the best. I like that height there. That's a little bit better. Okay, so in this triangle, you know that to find the area of a triangle, it's half the base times the height, right? And in this case, we could call C the base and H is the height. But we could say that H, we talked about this last time, that we could use sine for this little right triangle here without tracing over, just for the moment, just focus on that right triangle. And we know that the sine of angle A is opposite over hypotenuse. So sine of angle A equals H over B. And so if I solve for H, won't I get B times sine of angle A? Everybody agree? So that means I can replace the height, instead of calling it H, I can call it B times the sine of A. So we get this as a neat little formula for finding the area of a triangle that's not a right triangle, right? Area of an oblique triangle. And it's half of B times C times the sine of A, but you could say, oh, that's the same as half of A times B times the sine of C, or half of A times C times the sine of B. All of those are good and useful. So the area of an oblique triangle, to sum up, is 1/2 the product of the lengths of 2 sides times the sine of their included angle. So if we take, in this case, we were taking B times C, right, those lengths, times the sine of the included angle, and then times 1/2. All right, so that's that. Let's test this out now. Find the area of a triangular lot containing side lengths that measure 24 yards, 18 yards, and form an angle of 80 degrees. So in this case, we can use any one of these formulas, but let's just stick with this one, I guess. Half of B times C times sine of A, and we can call this B, this C, and this angle A. All right? Would you go ahead and work this out, please?
I got 212.7.
212.7, people agree with that? All right, so 212.7, and I guess what units would we be talking about?
Yards squared.
Yards squared, right? Because we're talking about square units, we're talking about area. Okay, and all right, that brings up something new. All right, this example. Let me pause the video for a moment. Here. Okay, so we're looking at this extra example, but before we can do that extra example, we're looking at page 355 in your book. And on page 355, it talks about trigonometry and bearings. In surveying and navigation, directions are generally given in terms of bearings. A bearing measures the acute angle that a path or line of sight makes with a fixed north-south line, as shown in figure 4.82. For instance, the bearing south 35 degrees east in figure 4.82 means 35 degrees east of south. All right, and then they give another example. Let's just look at the next one. I'll go back to this picture in just a minute. So if I have an angle that kind of is going off like this, and let's say this angle right here is 12 degrees, we would say, hey, this bearing is north 12 degrees, what? East, right? We all know our directions, north, south, east, west, yes? Okay, so what would be the bearing for, let's say for this one, let's say this angle here is 47 degrees. How would we classify the bearing or the direction for this angle? Alex?
So, 47 degrees east.
South 47 degrees east, everybody agree? And what if I have, let's say this one out here, and let's say, I'm going to try and trick you here. I'm going to say this angle right here is 10 degrees. Danny?
Not, it's north, and then 80 degrees west.
Yeah, I couldn't trick Danny. North 80 degrees west, because we're really always measured from the north-south line, right, not from the east-west. So this is heading north, but it's angled 80 degrees to the west. Are we okay with bearings? Awesome. So let's go back to, that's not us. Okay, let's go back to this example. In this example that I just gave you, which I set down somewhere as I was handing out. I have a whole stack. Honestly, I do have a whole stack.
What? Schools don't.
Okay, so in this example, it says on a small lake, a child swam from point A to point B at a bearing of north 28 degrees east. The child then swam to point C at a bearing of north 58 degrees west. Point C is 800 meters due north of point A. How many total meters did the child swim? So here's our picture, okay, and I probably have, too much information already on here, I can see that. Okay, so this is 800, and hopefully you were able to figure out that if the child is starting from point A and swimming to point B at a bearing of north 28 degrees east, that we can put the 28 degrees right here. Agreed? But then from this point, from B to C, the child was swimming at a bearing of north 58 degrees west. Would you agree that that's the 58 degree angle there? Okay? So that's all the information they give you, and you're supposed to find out the total meters that the child swam. So I think that means we need to find this length here. I'm going to call it C because it's across from angle C. And we need to find this length here, which I'm going to call A because it's across from angle A. Everybody agree with that?
Yeah.
All right. Okay, at this point, that's great, but I only know one side of this triangle, and really, right now, I only know one angle. Is there a way to get another angle in this triangle? Here. This one? Is this one going to be, this one right here? Not that one? Down here? Would people agree that this angle down here is 28?
Is it I feel like
Yeah,
it's a
because
right.
they are alternate
Alternate.
interior angles. So that's 28 and this is 58. So that's going to leave what for this angle? Since they're on a straight line, those three angles add up to 180.
180 minus.
180 minus those. So you guys have a calculator in front of you. What's that turn out to be?
94.
94? Okay, so we like 94 degrees for this angle. And then we can also find this angle. What's this angle going to be?
58.
Also 58, again, alternate interior angles, or you could get that by adding 28 and 94 and subtracting from 180, correct? All right, great. Now we know all three angles, and we need to find side C, and we need to find side A and add them together. Danny?
So it's sort of like they're supplementary angles, or sometimes they be complementary. Like,
Well, in this picture, the alternate interior angles were congruent, but these three angles here were all on a straight line, so we knew that they had to add up to 180. Right? Okay, so at this point, you would set up and solve, and I think maybe I'll leave you to do this. So you're going to do sine A over A equals sine B over B, right? Because we know, we're trying to find side A, but we know angle A is 28. So how are we going to set this up? What's it going to look like? Josh?
So it's gonna be sine of 28 degrees. So it should be over A.
Over A, because we don't know A yet, equals,
Equals 90, or sine of 94 over 800.
over 800. Would you go ahead and work that out, please, and see what you get for side A? You're cross multiplying and solving. Danny?
I got 376.49.
I'm going to go 376.5. Do people agree with that? Okay, people are nodding their heads. And then the child also then swam from B to C. So we need to find this side A. So, wait, that's what we found. But we need to find side C, right? Their first leg of this journey, Stephanie?
680.095.
How'd you get, what'd you get?
680.095.
How'd you get that?
Sine of 94 over 800 equals sine of 58 over C.
So that's sine of 94 over 800 equals sine of 58 over C. Everybody agree with that? And then when you cross multiply here, you said you got C equaling what?
Oh, I just did the 80 sine 58 over sine 94.
Okay, so, but we agree with this setup? So what's this gonna be when we work it out? Grabbing your calculator? What'd you get?
680.1.
680.1. All right, so altogether, I think the child swam 680.1 miles first, and then 376. So
Miles?
Sorry, meters. Good swimmer, very good swimmer. So you're going to say 680.1 plus 376.5, and we get our total number of meters. Meters is what?
Don't you have to add the 800 here?
I don't think that, it doesn't say that they swam back, but if they did, then you'd add on the 800.
Oh, okay.
Well, what is this?
1056.6.
1,560.
No, 1056.6.
Ah,
Oh, 45.
ah.
I got 40.
1,060.
Yeah, you're right here.
1,066?
No, 56.
I should have just kept adding myself. Okay, are we okay with this?
Yeah.
Awesome. So at this point, this is what I already told you about. Okay, so at this point, I would like to look at a few things from Law of Cosines. All right. Hello.
I can't really sleep in. Sorry to interrupt.
Okay, so we're looking now at Law of Cosines. So remember, there's two cases remaining. All right, we talked about Law of Sines works for two cases. Let me pull that back up again. We started off here. Oh, boy. All that good stuff. There we go. So we started talking about the four different cases, okay? Two angles at any side, that's like AAS or ASA, or two sides and an angle opposite them, which is SSA. Or three sides given, or two sides and their included angle. So what we've been handling is solving oblique triangles of case 1 and case 2 type. So that's the type where you're given, you know, two angles in any side or two sides and an angle opposite them. But we now need to say, well, what if it's case 3 or case 4? What if you're given three sides or given two sides and their included angle? In neither one of these situations can you use law of sines to solve. Law of sines will not work. So that's why we need to have this new helpful formula, law of cosines. All right, so our objective here is to solve oblique triangles using the law of cosines. And so this is the SSS and the SAS cases, all right? So these formulas here, not as easy to remember as your law of sines formula, but basically it's saying if you have, let's back up. So if we're trying to solve for a side in the triangle, let's say that side is A, but we know the two other sides, B and C, and we know the cosine of angle A, then we can say that A squared is equal to B squared plus C squared minus 2BC times cosine of angle A. Danny?
Is it similar to the formula that we use for the area? Like it looks like the last part, sort of.
So I think it's got some structure to it that's similar. Yes, looks similar to that area formula. But actually in this section we learn a different area formula. That's helpful. Yeah. You mean only memorize one of these?
Yeah.
Yeah, and I think I'm still going to provide you with this formula anyway. But you're right, it's just if you know two sides, you square them, add them together, and take minus 2 times those two sides multiplied times cosine of your angle A. But I would provide those for you. But that's the law of cosines if you're solving for a side length. But what if you're trying to solve for an angle itself? Then you would use one of these alternate forms. This is basically, let me back up for a second. This, if you take this equation right here and you solve it for angle C, or for the cosine of angle C, you will get this formula, right? We say, oh, I'm going to subtract B squared from both sides, I'm going to subtract C squared from both sides, and I'm going to divide by negative 2BC. And you'll end up with this, although you'll have A squared minus B squared minus C squared over a negative 2BC. But then how they get this? They just multiply, right, top and bottom by negative 1, and they got this. We're not ignorant. Okay, so alternate form is to help you if you're solving for an angle instead of a side. Okay, so let's take a look at an example. So this is an SSS case, meaning we're given the 3 side lengths in a triangle, but we know no angles. All right, and we're trying to solve the triangle, so we're trying to find the missing angles here. One side is 6, one side's 8, one side is 12. So would we use, what formula? Oh, you know what? They do recommend that you always solve for the largest angle first. So in this case, we're going to solve for which angle? C. So coincidentally, I can still see this on the same screen. So let's use that formula. Talk me through what we're going to do to plug things in here. Cam?
6 squared plus 8 squared minus 12 squared of 2 times 6.
2 times 6 times 8. Do people agree with this?
Yes.
All right. So you're pulling this up on your calculators and doing this calculation? Plus 8 squared minus 12 squared. Oops. Over 2 times 6 times 8. And did you get negative 0.458?
Negative 11.4.
Is that okay? Decimal, negative 0.458-ish? Okay. So what does that mean? I'm going to go with negative 0.458. We're here, so we've got, it's not letting me extend this at all anymore. That's okay. I need more room. This might be loud. Brace yourself. Oh, it's not. Okay. Center a new page. There it is. Okay, so we just found out that cosine of angle C is equal to negative 0.458. Is that right? Okay, so we need to find angle C. So how are we going to do that, Alex? Arc cosine. So C is equal to the arc cosine of negative 0.458. What's your calculator tell you about that?
117.258.
117.3. Yeah, can we go? Okay, so 117.3 degrees. Are we okay with this? So remember, if your cosine of angle C turns out to be negative, that means that the angle is more than 90 degrees, right? Because we're stretching into quadrant 2. Does that make sense? Where cosine is negative. Okay, so now that we found that largest angle at 117.3 degrees, you could use law of cosines to find other angles, but at this point, it's probably easier to switch back to what? Law of sines. Danny.
So, because we're using arc cosine, is there a chance we have no real solutions or?
Is there a possibility? There is a possibility of that, but you know what? If these three sides actually make a triangle, and if you know that from geometry, because the two smallest sides add up to greater than the largest side, then a triangle is guaranteed. Does that make sense?
Yeah.
But if I said, oh, I want you to find me solve this triangle where A is 1, B is 4, and C is 10, well, then I bet you're going to get some kind of error message when you find cosine of C, right? Because this triangle is not possible, right? These two sides don't add up to something greater than this. They won't meet, right?
Yeah.
Okay. You know, that was a really good question.
Yeah. Thank you.
All right. Okay, so let's, so we're switching to law of sines here. So what do we know? This is our situation right now. So how are we going to set this up? Hannah?
Sine of C, so sine of 117.3.
So sine of 117.3
Yeah,
over
over 12.
equals,
Sine of A over 6.
okay? So sine, I don't think it matters at this point, but you might want to keep going with the largest, I don't know, let's see. So sine of A over 6, we're trying, okay? So go ahead and cross multiply and solve here. Mary, did you get an answer?
26.4.
26.4. Do people agree with that? Yes? Alex, you're okay with that? Josh, you okay with that? You're looking confused.
I have 25.
I like the arc side.
Let's see. So we're doing sine.
I think you have to do arc sine. Yeah.
Are we okay? Let me just check this. So we're doing 6 times sine of, what was the angle?
117.3.
0.3 degrees over, what was my denominator? Just 12. And so I get 0.444, and then you did arc sine of that. So I want to do arc sine of that answer. You guys do that sometimes, control negative to pull up the answer. And I'm getting 0.46, but that was in radians. So I'm multiplying by 180 and dividing by pi. And I'm getting 26.4-ish. Okay, so we get 26.4 for angle A. And can we then just subtract the two angles from 180, Mary?
I just have a question. Can we
Yeah.
put our calculator and put it in degree mode?
Pardon me?
Can we just put our calculator in degree mode?
I thought we made a pact.
Oh.
That we were going to keep our calculators in radian mode. I would still keep it in radians. Just because I think that if we don't keep it in the same mode, I think we're gonna get messed up as we go back and forth.
I've been just doing with the book TV.
Yeah, okay, tell me about that. So let me go back up. So you're saying there's a shortcut?
Yeah.
Okay, let's hear about this shortcut.
Right when you get your answer done.
So like right here,
Yeah.
it gives me the, so this is radians, so 0.46 radians, and then what?
And then you go into the book thing.
The book right here,
Yeah.
okay?
And then do
And what about right here? Decimal degrees, the DD. I say enter, it's saying, oh, you want to convert that to decimal degrees? And it does, right? So that's maybe a faster way than saying times 180 over pi. All right, for sharing that. Nice catch. Okay, all right, so did you subtract then and find the last angle?
Yeah.
Yes, what'd you get for angle B?
It was 37 cleared it by accident. 36. Like something.
36 point something. Can we narrow that down?
Yeah.
What do we get? 36.3 degrees. Now remember, very important, more important than in law of sines, it's important here to check that your largest side is across from your largest angle and so on. So can you do that for me? 36.3 is here, and the 26.4 is here. 20, that's supposed to be a 26.4. So is the largest angle across from the longest side and smallest angle across from the shortest? Okay, all good? Awesome. All right, so that brings up this next case, the SAS case. This time we have two sides and the included angle. Again, impossible to solve this using law of sines. Just you don't have the right structure in place for this. We have to use law of cosines. And so at this point, we are going to have to use which of these formulas? Standard form, so like maybe one of these formulas. Let me get rid of this. Let's see.
Could we use any of the ones that we wanted? Like, could we use standard form or ultimate form because we could find an angle or
It'd be harder, but yeah.
Where are we at? Here we go. Okay, so we're using these, one of these formulas. Danny, did you get your question answered?
Yeah.
Yeah, you're okay? All right, so in this case, talk me through this. What would we use here? Let's see, Stephanie.
It would be 16 squared.
So which one of these are you using?
The top one.
Top one, okay.
16 squared plus,
So is this a squared equals?
Yeah.
16 squared?
plus 12 squared minus 2 times 16 times 12, and then cosine 80.
Cosine of 80 degrees. All right, go ahead and try that on your calculators, please. Okay, we are still recording for our friends.
And then you just square.
Take the square root, right? What'd you get?
I get 18.3.
18.3.
If I round it down.
Are we okay with this? 18.3 is this side. Okay, and at that point, if we have that, again, it might be easier to switch back to law of sines to solve. All right, so you're going to set this up and solve. I'm going to put a big dot, dot, dot on this one and let you finish this one up. Okay, let's see, what else do I have for you? I have some more good problems. Am I going to ask you to copy all this down? No, because I have this written over here. This one again, you might want to pass that tape back around and. Did the tape get passed around?
Yeah, I put it back. I like a minute. Yeah, Homer.
Summer.
Until lunch.
Okay.
I think this would be easier than it is.
No, he's not. He lost on the field trip.
Okay, so in this problem, it says in a softball game, a batter hits the ball to center field. The center fielder then throws the ball to third base as shown. The distance from the center fielder to home plate is 240 feet. The distance between the bases is 60 feet. How far did the center fielder throw the ball? Alright, so let's see if I can slide this on. Okay. So the batter hits the ball to center field, so it's out here somewhere. The center fielder then throws the ball to third base. So that's the D for the distance, right? And then the distance from the center fielder to home plate, they're telling us is 240. And the distance between the bases is 60 feet. So how far did the center fielder throw the ball? So we want to know this distance. So bottom line is we have this triangle here. I'm trying to draw this carefully, right? We have this triangle here. What do we know? We're trying to find this side D. We know this side is 60. We know this angle's 45 degrees, and this is 240. We'll take this up after lunch. No. Okay, so we are looking at this. We said we're solving this triangle in particular. Can you get the door, please, Cam? In particular, we're trying to find side D. So how would we set this up using the law of cosines here? Danny?
I set it up as a squared equals 60 squared.
So a squared meaning d squared in this case?
Yeah.
Equals 60 squared
Times 240 squared.
times 240 squared
I think is now plus 240 squared.
plus, that's supposed to be plus 240 squared?
Yeah. Minus 2 times 60 times 240 times cosine of 45 degrees.
Times cosine of 45 degrees?
Yes.
Everybody agree with this setup? Okay, so you're working this out.
What's he talking?
All right, what'd you get for your answer here? How much? 202.1. Does that sound right?
Yes.
202.1 feet that the center fielder throws the ball to third base. Are we okay with this? All right, so I think we're going to stop right now, and we'll handle that shift problem next time. But for right now, I want to get you into groups to work on something else.